Hey there, everybody. This video is about one-to-one functions and inverse functions more specifically. And so we have some, again, this one's a little abstract as well. We have what's called a conditional statement. It says that P implies Q, or if P, then Q. And a conditional statement is equivalent to what's called a contrapositive. So not Q implies not P. So we'll have an example. Here's the conditional statement. If it is raining, then there are clouds in the sky. So the contrapositive is, if there are no clouds in the sky, then it is not raining. I'll let you soak on that one for a little bit. A function is one-to-one if for every element y in the range there exists exactly one element x in the domain such that y is f of x. We'll show some more examples of that. And the main way that we tell if something is one-to-one or not is called the horizontal line test. Horizontal lines go left to right, and this particular graph passes the horizontal line test, meaning every horizontal line is going to cross it no more than one time. This function fails the horizontal line test. So this one is not one-to-one, this one is one-to-one. Two ways to prove that a function is one-to-one. You can assume f of x equals f of b, or f of a equals f of b, and then prove that a equals b, or you can go the other way. Assume that a does not equal b, and then show that the two y values are not the same. And these arguments are related. This is the contrapositives again. And I'm not going to get too deep in that. We're getting a little too abstract there, so we're going to move on here. So a function has an inverse function if and only if it is a one-to-one function. An if and only if statement is a logical statement that implies if one part, then the other, and vice versa. If the other, then the one part. So it goes both ways. It's a very powerful, what's called an if-then statement. What is the inverse of an operation to? So to adding, the inverse is subtracting. To multiplying, the inverse is dividing. There's actually, and you can see here, I have a radical function and a squared function that they are inverses of one another. And you can see on a calculator that it's laid out that way. Here we have x squared, and then right up, down here. Here we have x squared, and then above it we have the radical. You can see even the sine function and its inverse. The cosine function, the inverse tangent function, it's all there. Even here, later we'll be getting into logarithms. The inverse of a logarithm is 10 to the x. The inverse of a natural logarithm is e to the x. That we'll come back to those in a different video. So we are going to, two functions are inverse if and only if. Here's another if and only if statement. When we composite them, they cancel one another out. So here's another example of that. You'll see that the squared and the square root, they exactly both cancel one another out. And this fancy here means for all x's that are elements of the domain of G. And again, this is for all elements, for all x's that are elements of the domain of F. Basically, the G and the F cancel one another out to end up with the X here. So if you composite two functions and they completely collapse, you end up with X as a result, then they're inverses of one another. You usually don't need to do both, but I did both. So I'm going to do F composite G of X, and you can see when I put in G of X into X, you see the 3's cancel, and the minus 2's cancel, and we just get x as a result. Same here. When I put f, the function f, into g, and you can see I did that here, you can see everything collapses out, I just get x. And that verifies that they are inverse functions of one another. So here we are with two functions, and what we can do is we can actually put one into the other and show that f and g in this case are inverse functions. A better example of this is going to be a little bit lower here, and I'm going to kind of skip on from there. But here we have if f and g are inverse functions, then you can see all the domain values, the x values, all become the range values for the other. So the domain and range actually exactly swap out for one another with inverse functions. And you can see all the range values, the 4, the 8, the 10, become the domain values or the x values here. I want to caution you, this is the notation for f inverse. It looks like f to the negative first power. It does not mean that. It means literally the inverse. So once again, you can see on the calculator, inverse sine, that definitely doesn't mean 1 over sine, as we're looking at that. So just be careful. I want to show you two functions. Here we have a function root x, and we have a function x squared. It's been the domain has been modified, so the domain of this function is only 0 to infinity. And one of the interesting things that happens with inverse functions and their parent function is when we draw the graph, the line y equals x, you can see this is slope-intercept form. This is slope 1, y-intercept of 0, so up 1 over 1. And you can see they become exactly mirror images of one another against this line y equals x. That will always happen with inverse functions. So finding an inverse function, this goes back to the top of the page. And these are the main steps. First, we make sure that it's 1-to-1. If it's not, sometimes what we can do is limit the domain so that it becomes 1-to-1. You swap out the x and all the x's and the y's, they all become opposites to one another. Solve for y, and sometimes that's complicated and sometimes it's not even possible. And then when you're done, you're going to relabel y as f inverse of x. And to verify that they're inverses, you can actually composite them together. And once again, you can see that the inverses, the domain of the one is the range of the other and vice versa. And that all comes from here, swapping out the x and the y. So let's find the inverse function of this. This is a linear function. So rewrote f of x as y, swap out the x and y, and solve for y. And then replace the y with f inverse. So this is the inverse of this linear function here. You could verify that by compositing the two together, and they should collapse out and just get x as a result. Here what we do is we take the square root, we end up with plus or minus, and notice that they limited the domain, x is less than or equal to -7. So what's happening is, as we square both sides and swap out the x and y and solve for y, we don't need the plus or minus anymore. That means it's not 1-to-1 actually. And we end up with this, it actually means it's not a function. And so because y is less than or equal to 7, we can be assured that we're here. Cool stuff. Next up, here I rewrote f of x as y, swap out the x's and the y's, and solve for y. And you can see here's a radical function again like we had before, and we end up with a parabola, which is going to be its opposite or its inverse function. And you can see that we're going to have to be careful with our range values and our domain values as we look at this. Here's another one. I can square both sides. That gets rid of the negative, but it becomes quite telling here of where it is that we go with this as far as what range and domain values we have. So square both sides, solve for y, and we end up with f inverse of x equals x squared minus 4.